Okay, give you a little background on the work we've been doing. The Excavation and Mobility Modeling Project is part of the NLSI project, Scientific and Exploration Potential of the Lunar Poles. And the project goals are to develop discrete element method models of machine regolith interaction to enable this list of things. Simulation of lunar excavation and mobility scenarios, to relate Earth-based tests to lunar and planetary conditions, design next generation equipment, create virtual training environments, and plan future lunar and planetary surface operations. In this talk, we'll report on the project status. This is into our third year, and the results of model application to analyses of terrestrial Mars wheel digging tests and in situ Mars scuff tests. So the motivation of this work is to describe lunar and planetary soil mechanical behavior and describe complex machine soil behavior. We're attempting to develop a physics-based discrete element method model, and what I'm showing here in these cartoons are the discrete element, general method of the discrete element, where you would have a discrete particle system where the individual soil particles are defined as unique entities, and then the forces interacting at the contacts determine the behavior of the bulk material or the aggregate of material, and these forces are kind of defined here in terms of the forces at the contact and the moments that are generated. The thing that's very nice about the DEM is you can start capturing some of the granular material behaviors that are different than continuum behaviors. And an example is shown here where you get these shear slip planes that occur in soils that are difficult to replicate in a continuous system. So why do we use the DEM? One is because it handles large deformation and progressive failure of granular media well, and you can capture multi-scale processes fairly well. And I described some of these here, processes at the grain scale, percussive penetration is an example, wheel tread and cleat interactions with the soils, and then excavation processes, and I show a few pictures of those here. And also to provide improved parameters for large-scale continuum models, because there are scales at which DEM is not practical because of its computational restrictions at the moment. Our approach is to conduct physical experiments to guide model development and to validate our simulation accuracy. Physical experiments are listed here: mobility, excavation, geotechnical properties, micromechanical and tri-axial tests, and penetrometry. And in excavation, we're interested in both static and percussive penetration or excavation, primarily because on the moon you can't have the large masses that you use for terrestrial excavation, so you have to come up with ways to reduce the forces needed to do the excavation. In terms of the model development, we're trying to make a scalable model that runs on parallel supercomputers, maximize algorithmic efficiency, incorporate realistic shapes and contact physics, and be able to scale from laptops to massive computer or supercomputers, and also from small to large scale problems. This is sort of a cartoon of how we developed the DEM. So you have test beds to run your tests. You have the simulations. So this is of a wheel. These are of tri-axial tests, and then you can do microscale tests to get to actual contact properties. I'll talk a little bit more about some aspects of that later. This is an example of some of the particle set that you can have. DEMs initially started out with spherical particles, but those aren't very representative of soils. And here we have an example of JSC1A coarse grains and some representations that we've used to try and simulate that. These being smooth polyellipsoids that you can get some complex shapes with, and these are more angular polyhedra, and these are more geometrical polyhedra. So this is an example of our quasi-static excavation tests and our simulations that we're putting together for those. So here's the test bed, the excavator, and if you look closely, you can see some little red laser lines there that we're using to examine what the heap shape is. So we not only have force information to check against the model, but we also have deformation information as well. So the heap, this is shown a little bit better here, where you have the heap here, and there's a red laser line that runs there, and these are some of the heap shapes that have formed during the excavation. And here are some of the forces. So forces in the X direction, Y direction, and Z direction. And this is the start of our DEM model that's currently under development. This is an example of percussive excavation in our test bed setup. So this is the percussive excavation device, and this is the actual scoop, and it applies a set force that you define at a set frequency that you define. And here is an example of how the force in the z-axis here varies as a function of impact frequency. So at static levels, this is the force it takes to excavate, and as you increase the frequency, that excavation force goes down significantly. So there's a lot of interest in using this kind of technology in low gravity situations. And this is another example of, so this would be the average force, and these are the maximum forces that you would see. So it takes quite a bit of frequency before you start getting that decrease here. If we look at the penetrometer simulation, so the previous two I said are under development. This one we've started doing some qualitative testing to get an idea of how we want to go. So this is the penetrometer setup at Glenn, and some of the tip resistance of the penetrometer as a function of depth is shown here. And this is a DEM simulation that is generating the force structure, and we've done it for two different density sets. So this is one, and this is the second one. And these are the force curves that we've gotten for those. These are just spherical particles to save computation time and get some experience with running it. Okay, we also have done some simulations of a rover wheel digging into lunar regolith, and this one I'm calling our quantitative model because we actually have measurements for the torque and the sinkage of the wheel, and we've got measurements for the internal friction of the soil from the experiments that we now compare with our DEM simulation. So here's the actual experiment, and it generates a torque signature along with sinkage. How do I run the actual movie? Can you, on the upper one? Just no, on the right, just select it and click on it. The upper right. Okay. It should run. There. Okay. Well, that's not running super. So we have the actual experiment, and then we have the DEM simulation. Can you start the other one too, please? And so this one would be with polyhedra particles, as I showed you before, and this one would be, polyellipsoids, and this is polyhedra, the angular type. And so basically we try and, with the simulation, get the best agreement we can to define the DEM parameters here from the bulk measurements. And so this is for the polyhedra test, but the similar thing is done for the, for the polyellipsoid test, but the similar thing is done for the polyhedra particles. So the other piece of this is the tri-axial cell experiment. Could you go over to the lower left and click on that, please? Just a quick discussion of how that works. If you load it, this has a rubber membrane around the grains and has a pressure applied to the side, and then you put a force on the top, and it'll deform it. And so when you run it at different lateral pressures, at different forces, you get a series of deformation curves. A series of deformation curves at those densities here, at those different confining pressures. And then from that, you can use a Mohr circle analysis in order to generate the circles from the principal stresses, where this is the lateral, this is the primary principal stress and the secondary principal stress. And then by fitting a curve to the tangent of those, you can come up with an internal friction value. And that's typically what people get from most of these tests that they do on the moon or the like, or on Mars. But internal friction is a fairly limited number to know about a soil. What you're really interested in is this behavior, the stress-strain behavior. And what some people will do is take internal friction and then try and create an algorithm that can generate that. But in this system, you can actually determine that based on the DEM simulations. Okay. So the analysis procedure is shown here, where you have the experiment that gives you the data. You match the data with you simulate the data as best you can. You then put it into your DEM simulation, generate the stress strain curves, generate the Mohr circles, and then get your internal friction angle. And when you look at the comparison of results, this is what you get from the wheel digging experiment, this is what you get from tri-axial cell experiments, and these are the values you get from the DEM. So we bracket them quite well. Now we've actually applied it to a Mars situation as well, and this is a scuff wheel test. And since I have my monitor over here, I'm going to kind of go through this fairly quickly. This is the DEM example of the scuff. These are the tri-axial simulations of this scuff situation. And so this is the actual data. So we have a sinkage of 25 millimeters at 11 Newton meters or 12 Newton meters. And these are all our runs, and the one that matches the best is this polyhedra at 26, but we're still a little bit low. And we get a 40-degree internal friction value, which is a bit higher than what people predict that to be. But there's no other way to get this kind of information on Mars with that kind of scuff, because it's just a single wheel rotation and it's not enough information to traditionally evaluate it the way they would by looking at angle of repose or the torque data from the wheels. So the status is we've completed the penetrometer excavation mobility tests. We have DEM model developments at different stages. We've added complex particles, improved model interface and computational efficiency, and we have planned, and these are our plans for this next year. And that's to continue the simulation of the physical tests to turn them from in development and qualitative to final stage. And if you want to learn more, we actually have 5 posters and 2 presentations, this being one, at this conference, so you can learn more from visiting those. Thanks.
We've got time for a quick question. Jim.
Your SSC about restoring a set of
At SSDC, we're just about finished restoring a set of penetrometer data from the Apollo missions. Would you have any interest in having that to compare with your penetrometer tests for these simulants?
Well, if we have the force history of how the penetrometer was put in place, then we probably could do that.
Okay. Yeah. Okay. But I should talk to you. I'll tell you what they did. It's not going to be quite as systematic as what you have, but it might be useful.
It basically is if it's like ours is a constant velocity here, and so if theirs is a dynamic penetrometer, we have to know what the momentum is that's going into the system.
This is astronauts pushing a thing into the ground.
Yeah, that's tougher.